Hi, everybody. It's Dr. Lundholm, and we are here in the middle of section 3.5, I believe, looking at implicit differentiation. The first example we're going to look at today is example number 3, which is hopefully where we left off last time. Here's the problem. We are trying to find the derivative dy dx for this implicitly defined curve where all the x's and y's are, lumped together, and it's not easy, especially for y, to solve for y in terms of x. All right, so use this derivative to find the equation of the line that's perpendicular to the tangent line at the point 3, 2. So we're actually going to find the equation of this normal line. At what points does the curve have horizontal tangents? Okay. So the big thing for this problem, let's go ahead and try to find the derivative dy dx. And we're going to use implicit differentiation. Sorry, this just jumped. Here we go. Let's go ahead and just write that down so we're all on the same page. Okay, 3 minus y cubed plus y squared plus 5y minus x squared equals 0. Now we're going to take the derivative of both sides with respect to x, and we're going to treat y as a function of x. So taking the derivative of 3, 0. Taking the derivative of minus y cubed would be minus 3y squared. But according to the chain rule, since we're treating y as a function of x, some function that we don't really know, we're just going to multiply by, we could either write y prime or we could write dy dx here. Both of those mean the same thing. But that's, yeah, according to the chain rule. Likewise, we'd have 2y times dy dx for the next part. For the next part, we would have 5 times dy dx. And then we'd have minus 2x and 0 over on the right-hand side. Now we can collect all of those terms that we have dy dx, pull that out front. So we get minus 3y squared plus 2y plus 5. And I'm going to bring the 2x over to the right-hand side. And now, in order to solve for dy dx, we just divide both sides by that quadratic expression, and we get 2x over minus 3y squared plus 2y plus 5. Yeah, and this one looks weird because we've got x's and y's as inputs into this derivative, but that's exactly what we're looking for when we do this implicitly. What this means is, now we have a derivative, and if we wanted to evaluate this derivative at the point 3, 2, it would be pretty easy for us. I believe this is the notation that would be used in our book. Yeah, this is the derivative evaluated at the point 3, 2. And we could just go ahead and, put those in. 2 times 2 over negative 3 times 3 squared plus 2 times 3 plus 5. 4 on the top, and negative 27 plus 6, so that'd be negative 21 plus 5, negative 16. All right, so we're hoping for a slope of 1/4, and that doesn't seem right at all, because I put the wrong things in. Boy. All right, I'm sorry. I'm erasing this. No edits. All right, what I did is I plugged the x value in for y and the y value in for x. My bad. Hopefully you caught that already. The x value is 3 and the y value is 2. All right, so 6 on top, that makes a little bit more sense. So minus 12 on bottom, plus 4 gives us minus 8, plus 5 gives us minus 3. And getting a slope of -2? Does that make more sense? Yeah, that looks more like the slope of that red line. So I'm cautiously optimistic. Let's go ahead and check out GeoGebra to make sure we're on the right track. All right. So I have already input our equation in here. Let's make this easy to read. It's already at 28. We're good. That's our original equation. And I nicknamed the derivative that we found as m of xy. And notice that if I click this, there's a color that comes here, but this derivative is not graphed anywhere here because this is a multivariable function. We're putting in x and y. And if we wanted to visualize this derivative as a graph, well, we'd actually need to, throw in another variable like z and, visualize this in 3D space. That's something that we'll do in multivariable calculus in Calc 3. But for right now, it is serving as, like a handy formula where we'll be able to plug in a point, x, y, and get out the slope that is at that point. Okay, so what we wanted to verify is that at this point, where we have the point 32, that the slope of the tangent line at this point would be -2. So what we could do is, I've done it here using, putting in m of 32 to get the derivative and multiplying that times x minus 3 plus 2. This is like our tangent line formula where you multiply the slope times x minus an x value plus the y value. But let's go ahead and build it real quick just for 3-2. I made those other ones a little bit more general. So let's call this one L. We'll call this line L of x. And what we would do is we could put in m of 3-2, but we should get -2 out of that. Our slope is -2. I'm just going to write it here. X minus our x value of 3 and then plus our y value of 2 gets us this tangent line. It looks great. So tangent line, solid. They asked us for a normal line, however. If we wanted to do the normal line well, again, I've done that here using the formula for m up here, but let's go ahead and just try this. I'm going to call this one H for funsies. I don't know. But instead of a slope of -2, we would want the opposite reciprocal for this slope. So just changing this to 1/2 would be great. We're still centered at the same anchor point. So still using an x value of 3 and a y value of 2 gets us that normal line. So solid. If we go back and, look at the problem, come on, there we go. Yeah, the equation for the normal line we could call it normal line, but 1/2 times x minus 3 plus 2 gets us there in terms of being a line. And then at what points does the curve have horizontal tangents? A horizontal tangent line would mean that the slope is equal to 0. So if we wanted to do horizontal tangents, we would set this equal to 0, and our derivative is equal to 0 precisely when x is equal to 0. The numerator is equal to 0. So that would mean that x is equal to 0. And that's why we see that we have a flat slope here, where x is equal to 0. And I guess one of the things that you'd want to watch out for is you wouldn't want the denominator to be 0 at the same time, because then you would be, in an indeterminate form. Yeah, it totally makes sense for this one that we have a horizontal tangent line. This is interesting. Let's go ahead and put the point in 0, -1 and see what happens. I mean, it should be 0, -1 should be a point that's on this curve. If we plug that into our function, sorry, our derivative, let's use this white space up here. If we evaluate our derivative at the point 0, -1, because right now 0, -1 kind of looks like iffy. That's not a slope of 0. So what's going on? We'd have 2 times 0 on top, and we would have -3 times 1 squared plus 2 times -1. Sorry, this is all -1. And then plus 5. Here we would have 0 over -3 minus 2 plus 5. So we do have an indeterminate form of 0 over 0 at this point. Good grief. And it went off the screen as I wrote it. So yeah, our derivative has an indeterminate form there. And in order to evaluate what's happening at this specific point, we might want to employ, I don't know, some beefier rules, like maybe L'Hopital's rule that we'll learn about later, in order to, evaluate what that derivative actually would be. I guess one of the things there is that at that specific point, the curve intersects that point twice. And that's pretty unique out of all the points from that graph. So that's maybe one of the reasons why it's not differentiable here. If we were thinking about, taking the derivative, it would have a slope that, is negative this way, but also positive this way. And so maybe it's just not differentiable. I don't know. It's kind of cool to investigate that, but we're going to have a horizontal tangent where x equals 0. And up here, where y equals 3, the bottom part's not going to equal 0 at the same time. So it would be completely fine. Okay, moving on. I think we explained that one into the ground. Example number 5. Here we're going to take the second derivative of this circle. So we've got the unit circle here. If we take the first derivative, we could do that implicitly. We would have, and if we're doing this with respect to x, we'd have 2x plus 2y times, well, y prime's nice because it's shorter, but again, this problem is kind of phrased in the dy's and the dx's. So I'm going to write dy dx there, and then equals 0. Solving for dy dx would mean subtracting 2x from both sides. And then dividing both sides by 2y, which just leaves us minus x over y for our first derivative. This is the first derivative. Finding the second derivative means that we're taking the derivative of the derivative. And that's why the notation on the left-hand side turns into d squared y over dx squared. It's because the d over dx part, the derivative operator, is the thing that's repeated twice, and y is just chilling. But yeah, on the right-hand side, we're going to need to take the derivative using implicit differentiation. And since minus x is a function of x and y is a function of x, we're going to use the quotient rule here. So maybe I even write that. Quotient rule at this stage. Low D high. So the derivative of the top is -1. And so we've got minus y for the first part, and then we're going to subtract high D low. So subtracting -x means that we've got plus x, and then we're multiplying it times the derivative of the bottom, which is y prime. Or I've been using dy dx this entire time. So we're going to stay consistent all over y squared. And so, technically this is the derivative of the derivative, but in order to get it all in terms of y's and x's, it would be good to make a substitution from this step in for dy dx. So we get to the stage where we've got the second derivative is equal to minus y plus x times minus x over y all over y squared. And to simplify this, maybe one step further, let's go ahead and just go to the right. If we multiply the top and the bottom by just a y, then we'll get rid of this denominator, and that's going to be good. So if we multiply through everything by y, we would get minus y squared, minus x squared on top, and all over y cubed on bottom. And pulling out a negative, that means that we've got x squared plus y squared on top. Whoops. So that's y cubed on the bottom. But since we're on this circle, and for this circle, x squared plus y squared equals 1, we can simplify this even one step further and say that -1 over y cubed is the simplest way to write the second derivative. And so, yeah, I think that I made a GeoGebra thing for this. So we could take a look at it quickly. Not that one, not that one. Oh, here it is. Cool. All right, so here's our unit circle. I plotted a point using the cosine of an angle, W. W goes from 0 to 2 pi. But I used cosine sign just to make sure that we're at a point on the unit circle. That's an easy way to get X and Y values here. So I can make it go nice and slide around. But I also put in for V of XY, that's the first derivative, and A of XY, that's the second derivative that we just found implicitly. We could make a tangent line using our first derivative. That's pretty cool. This one is a line that's describing the second derivative and how, I don't know, that the derivative is changing. So I guess one thing that you might want to look at is on the top of this, where the Y values are positive, the slope of this line, as you're going from kind of the smallest X value to the largest X value, the slope is constantly shrinking. It's starting off at something that looks like positive infinity. It's a smaller positive number looks to be 0, negative number, slope still negative, and then basically goes down to negative infinity when you're thinking about it that way. So, yeah, when the Y value, which is the only thing at the bottom of the second derivative, when that's positive, the value of the second derivative is negative. Here's the value of that second derivative. Okay. And when we're on the lower part, we're starting off at a slope that's akin to negative infinity, and then getting larger and larger slopes all the way over. So on the bottom part, negative Y values turn into positive rates of change of the slope. Okay, so what we figured out makes some sense. We were able to make a nice tangent line with this, and then think about how the slope of the tangent line is changing as you move around the circle. All right, let's go back here and jump into section 3.6. Here we're going to look at the derivatives of inverse functions. So hopefully we remember some stuff from chapter 1 where we talked about inverse functions, I think in 1.4. One of the main things to remember right off the get-go is when you have a function f in blue, the inverse function is going to be the mirror reflection around the y equals x, because the way that you plot inverse functions is you exchange the roles of x and y. So when this point on the blue function is CF of C, this point mirrored is F of CC on the inverse function. And so there's a cool relationship here where the slope of the tangent line for our normal function is just given a slope m. But when you look at the slope of the inverse function, the slope is 1 over m. And similarly for the y-intercept, we've got a y-intercept of b. Here we've got a y-intercept of negative b over m for the inverse function. That is cool. What we're going to do is find formulas for finding the derivatives of inverse functions using implicit differentiation. So this is kind of the definition, or at least an important property of inverse functions, that whenever you compose an inverse function and the original function, whether the original function's on the inside or the original function's on the outside, the property is that when you compose those two, you end up getting x right back out. So whatever you input, you end up getting directly as your output. But we get two different formulas for finding the derivative of inverse functions if we take these through and do implicit differentiation along the way, utilizing the chain rule. So on the left-hand side, we're taking the derivative of both sides, and taking the derivative of this part, we're doing the chain rule. The chain rule looks like taking the derivative of the outside function, evaluated at the inside function, times the derivative of the inside function. So that's chain rule right there. And then in order to get this version of the formula, all we're doing is dividing both sides by f prime. Similarly, rewriting those in the opposite order, taking the derivative, doing the chain rule, we get another version of the formula where, here we've got an x value as the input into the inverse function. Here we've got a y value as the input into the inverse function. And so depending on the circumstance, one of these might be easier to utilize depending on the information that you've been given. And here we are, example 1. Let's try to utilize this. What's nice about these formulas is that you don't actually have to, take the derivative of the inverse function per se, because that's what this gives you. But, for instance, on this one where we're given f of x equals x squared, and we're meant to find f inverse prime of 4, we're in this kind of a situation where, let me go ahead and I will color code this. Hopefully that syncs up soon. But yeah, we're in the situation where we're plugging in an x value. And so in order to figure this out, we're going to need to figure out the derivative of f and the inverse of f. But we can utilize that information to get the derivative of the inverse. So one thing that we'll want to know is the derivative of f, which is just 2x. We'll also want to know the inverse of f, which if f is x squared, the inverse of the square root of x, at least for that part of the domain, is great. And since we're putting in a positive x value, it makes sense to use this version. But yeah, once you have that, for part A, the derivative of the inverse function is 1 over On the outside, we've got the derivative of f, and on the inside, we've got the inverse of f evaluated at our x value 4. So we're going to have the inverse on the inside. So that's f inverse of 4. And this is what it looks like when you compose them. That's just 2 of x, or sorry, 2 times x. And when you work this out, you get 1/4. Yeah, this is kind of a long way to say that when you find the derivative, or like the slope of the tangent line of the inverse function, which is the square root of x, at x equals 4, the slope of that tangent line is going to be 1/4. I think I made a thing on GeoGebra. We can just look at this real quick. F is x squared. F inverse is the square root of x. And then the derivative of the square root of x is right here. And so, yes, we could make a tangent line right there. Let's call this big old T of x. We'd need the slope. And so we're hoping that the slope's going to be 1/4 x minus 4 for the x value, and then plus 2 for the y value gives us a tangent line on our inverse function. So 1/4 is the right thing. This new way of calculating it, I don't know, could be kind of bothersome, but allows us to find the derivative of an inverse function without actually finding that function explicitly. Yeah, it would have been, pretty easy to take find the inverse function and then take the derivative. You'd get the same thing. But the function won't always be kind of this nice and simple. And for part B, we would use this other form because we are determining, the derivative of this at the point g of 2 as an input. So what we would do is, real quick, let's just do it. We would find g of 2, and that would be 2 to the 5th minus 2 squared plus 5 times 2 minus 7. So it's 32 minus 4, which is 28, plus 10, which is 38, minus 7, which is 31. And so, we would be plugging in 31 into, if we wanted to find the derivative, of g inverse at 2, we would have 1 over the derivative of this function evaluated at 2. So maybe I didn't even need to figure out g of 2 this time. Maybe that's what we're hoping to avoid. No, this should be 31 here. We found that was our y value. So that's what we put in there. 1 over f prime of 2 then, and, or sorry, not f prime, g prime. But yeah, we would need to evaluate g prime of 2. Oof. G prime of 2 would be 5 times 2 to the 4th, just using the power rule here, minus 2 times 2 plus 5. And I guess that would be the end of it. So this becomes 5 times 16, which is 80, minus 4, which is 76, plus 5 is 81. So hopefully, yeah, the slope here of whatever the inverse function of this polynomial is would have a slope of 1 over 81 at the point g of 2, or 2 comma g of 2. Well, yeah, g of 2 comma 2 if you're on the inverse function. Anyways, that's a cool thing. You'll do a few of those on your homework. 2 ways to look at it, depending on whether you're putting in an x value or a y value. Let's keep going. This one's actually cool. This is actually relevant. Sorry that this one was kind of lame. The ln of x is an inverse function, and finding the derivative of said inverse function is possible through the power of implicit differentiation. One of the ways to look at our function that we would like to take the derivative of would be y equals ln of x. But equivalently, which I might write in here, this would be e to the y is equal to x if we raise both sides of that equation with e as a base. So this is just an alternate way to write this, but now using implicit differentiation and the chain rule, we're treating e to the y as a function of x, so that we have e to the y times dy dx, and the derivative of x on the right-hand side just becomes 1. Dividing both sides of this equation by e to the y gives us 1 over e to the y, but remember, e to the y is equal to x, and we're able to just make that substitution back in to get a nice cleaner formula for the derivative. And that's actually a cool way to show that the derivative of ln of x should be 1 over x. And yeah, very similarly, when you're looking at log base a, that's just off by a factor of 1 over ln of a, but it's still 1 over x is the main function. Cool. Example 2. All of these would be just kind of exercises in doing the chain rule at this point. I guess it would be getting a feel for this new derivative rule that we just found. I don't know, we could do one of them. Let's do A. A is actually, it's the most simple to do algebraically, but it probably has the most value in terms of realizing that there's something cool going on. So let's just do this one real quick. For part A, if we're going to take the derivative dy dx We could use the chain rule, where ln of x is the big function, k times x is the small function. So we would have 1 over k to the x for the derivative of the big function times the derivative of the small function, which is just k. But notice that here we would have k in the denominator and k in the numerator, so that we end up just getting 1 over x. And that might be surprising. But if we take a look at this, now I didn't make this on GeoGebra already, but we can look at this on GeoGebra. Let's just open up something new. I don't care, get out of here. The ln of k times x should make k as a slider. Excellent. Here's just the normal ln of x, but changing the k on the inside of here, by laws of logarithms, this is the same thing as, this is equal to ln of 1, or sorry, ln of k, which is 1 right now, plus the ln of x. So let's do this. Same exact line, and it's going to remain the same exact line. But when you change this k, all it does is vertically, oh geez, you don't want to go, we don't want to go in a negative. Don't worry about that. Let's keep k positive for now. All that is a vertical shift. And I don't really want to start putting in negative numbers in for x. The implied domain here is positive values of x. But yeah, that's why the slope is the same, because I don't know, even if you were to multiply the x on the inside by 2, effectively all you've done is shift the graph vertically by ln of 2, and the slopes are still the same even if you vertically shift the graph. The slope doesn't change at any given x value. So that, I don't know, that's kind of cool. The last thing that we need to talk about today, I think, is, well, all right, second to last thing, sorry, is logarithmic differentiation. Sometimes you get crazy looking expressions like this with interesting combinations of powers. Here we've got a square root function over a cubic. Here we've got 3/2, 1/2 to the 4th. Technically, for either function f or function g here, we could solve that using the quotient rule and the power rule and the chain rule. It would be a lot to do all at once. Like, for instance, on this one, it's a quotient rule because there's a quotient, but there's also a product rule on the top. And within that product rule, there would be 2 chain rules, one for this one and one for this one. So keeping track of all of those rules would be pretty crazy to do. And one thing that could make it possibly easier would be using this new technique called logarithmic differentiation. And honestly, it's necessary to take a derivative of something that looks like this, where we've got x to the 2x. That's a weird looking function. The steps for logarithmic differentiation look like taking a natural log of both sides of y equals f of x. And what that does is it changes the powers that we see here into kind of coefficients, because log of an exponential expression is the same as taking the exponent out to the outside and multiplying it times log of x. So there's a nice simplification where powers become factors on the front. So we would essentially be able to bring powers down and things work out nicer. I think to show you all the steps of logarithmic differentiation, I think we'll look at part C, because that's like the new type of function that you could really only do using logarithmic differentiation. But the idea is, once you take the log of both sides, you differentiate both sides implicitly, and then you solve the resulting equation for y prime. Let's try this real quick. So here we've got h of x equals, nope, x to the 2x. Take the natural log of both sides. So we've got, oh, and h of x is going to turn into y. Sorry. That'll be easier to keep track of it. Take the natural log of both sides. So we get the natural log of y. And we take the natural log of x to the 2x, so that it's, yikes, nice to now treat this as 2x times the ln of x. And so you see this thing where we had exponentiation has become into something that's looking more like, okay, we'll need to take a product rule, but that's something that we can do. So if we implicitly differentiate now on both sides with respect to x, on this side, we're going to have 1 over y times y prime for that natural log. And then on the right-hand side, we're going to have a product rule. So let's take the derivative of the first, which is 2 times the second, which is ln of x, and add that to the first one times the derivative of the second one, which is 1 over x. And so we get 1 over y times y prime equals 2 ln of x plus 2. That simplifies nicely. And then solving for y prime means that we've got y prime equals y times the whole mess that we had on the right-hand side. And that's fine for implicit differentiation, but remember, we can actually make this a little bit nicer, because initially we defined y to be x times 2 to the x. So if you were, hoping to have a function completely in terms of x, it's possible. Yikes. It just looks like this. So that's a little bit gross, but it is what it is. And we've now grown to have new powers. We're able to find derivatives of functions that look like this now. That's cool. But again, logarithmic differentiation, we're only going to put it into practice when things look really rough. When we've got, I don't know, really gnarly expressions to take the derivative of. The last thing for today is inverse trig derivatives. And so we're looking at the derivative of arc sine or arc cosine, that kind of thing. And what we see up here is coming from the inverse function derivatives that we looked at, towards the beginning of things. We're looking at these two formulas. But what inverse trig derivatives really come down to is building a triangle based off of angles that you're trying to find. So using that formula that we had before, we get the derivative of the arcsine should be 1 over the cosine of the arcsine of x. The arcsine of x asks us, what is the angle where the sine is equal to x? And so what we can do is build a triangle where the sine of theta is equal to opposite over adjacent. No, sorry, opposite over hypotenuse. What am I talking about? And that's not writing, so it'll be there eventually. Sine of theta is equal to opposite over hypotenuse, and the opposite is x, and the hypotenuse is 1. And so that would be the thing that dictates the triangle. We're building a triangle where the side is equal to x over 1. And because we have 1 and x already, we're able to find that the adjacent leg is the square root of 1 minus x squared just by the Pythagorean theorem. Hopefully, eventually, this is going to show up. I don't want to write too much more. But yeah, if you're thinking about the Pythagorean theorem, you would have c squared is equal to 1. Okay, here, let's look at the Pythagorean theorem. I don't know, maybe we call this one B, and this one A, and this one C. You know, A squared plus B squared equals C squared for the Pythagorean theorem, turns into x squared plus B squared equals 1 squared. But solving for B means that we get the square root of 1 minus x squared. Yeah, for that third side. But what this allows us to do is deal with this composition of an inverse trig function and a regular trig function so that the steps look like, you know, what is the angle when the sine is equal to x? Well, the angle, just as we built this triangle, is theta. So the angle is theta, and then taking the cosine of theta means that we're looking at adjacent over hypotenuse. And adjacent over hypotenuse is just going to be the square root of 1 minus x squared. So the derivative of the arcsine ends up being 1 over the square root of 1 minus x squared. For this reason, we've used the inverse formula that we came up with earlier on, and we made this triangle to sort out the sines and cosines. And very, very similarly, all the other, you know, inverse trigonometric functions have derivatives that look pretty similar. You know, arcsine, arccosine, arctangent, arccotangent. These are ones that it's good to remember back that this whole thing of making a triangle and chasing this down is the reason why they look like 1 over some square root expression. But do I have all of these memorized? No, I do not have all of these memorized. These are something that I would look up when, you know, the chance arises. So, yeah, I mean, it's good to look around and see if you notice any patterns, but I don't have those memorized, so I'm not going to ask you to memorize those necessarily. And then this would just be an application of those. And if there's still time, go ahead and try some and see if you can apply, you know, finding the arc cotangent, and the arc secant. And if there's not time, no worries. This is just the chain rule using these formulas, so it's not a huge deal. All right. I think that I'm too long. I think that the video's gone too long. It's already 5:35. I hope that you guys have a good afternoon, and I'll see you tomorrow. All right. Bye.